We are rolling. Okay, so it says the water's volume does not change at a constant rate with respect to time. We said as time goes by, the volume filled up is slowing down, right? It's filling up with a fast volume at first, and then the changes in volume are slowing down or getting less for the same amounts of time. Okay? Does the water's volume change at a constant rate with respect to its height in the tank? So if you're looking at changes in height, are those proportional to changes in volume, regardless of the time it's taking to fill or the change in speed of the water height? So is the volume, does it change at a constant rate with respect to the height? She says yes. He says yes. Yes, it does. Because you're talking about the proportionality of the changes of those. Is a change in volume proportional to a change in height? And why is it in this tank you have that proportionality of changes in volume to changes in height? What is it about that tank that guarantees that? Yeah?
Well, because the radius is at no point does it become slimmer or wider.
Right.
So at all times the height will be, the water is just on the same radius.
Yeah, it's because the radius is fixed. That kind of a cross-section, a horizontal cross-section stays the same the whole way. So for any given change in height, you're going to see the same change in volume no matter where you see that change in height. Okay? So dV is going to be a little change in volume. dH is going to be a little change in height. So we can draw that. So we can think of a little change in height and the resulting change in volume. So it's going to be just a little teeny change in height like this. I should have done blue. All right? So we got this little, like it's like a real skinny pad of water. Okay, that's how we can kind of imagine dV and dH. What is dV? The volume of that, the little teeny volume, corresponding to a little change in height, dH. And so how are those related? This is a cylinder just like this is. It's just a really, really flat cylinder. So its volume is the same as the formula for a cylinder, which would be pi r squared. So the volume of a cylinder is pi r squared h. Well, when you think about little volume and a little h, it's also a cylinder. A little teeny h and a little volume is also a cylinder. It's just like a pancake instead of like the pipe. So the change in volume is going to be pi r squared, the change in height. So that's how you can express dV in terms of dH. That's part C. Okay? Why is it important that the water's volume changes at a constant rate with respect to height? So why is that important? It's important because whenever we're talking about differentials, we're talking about that those quantities vary with constant rate of change over whatever interval we're talking about. So when you're talking about differentials, you're talking about some interval of, in this case, h, where you have constant rate of change. So it's, why is it important? Because dV and dH imply that you have constant rate of change for a small interval of h you're talking about. Okay? How is V different from dV? So in part E, what is V? V is the total volumes filled in the total volume of water in the tank, in the pipe. Or tank, sorry. And dV would be a little change in volume, like I drew. So you have a total volume, and then a dV would be a little change in volume. Any questions on number 4? Can you ask a question if I lost you, or did I hit on the difficulty in this? Yes, please. Yes, but I think maybe in this question there, like, it's the meaning. What's the difference in the meaning of V versus dV? So differential is what we call it. So how is that different in meaning? So V would be the total volume in the tank, and then dV would be a little change in the volume. Other question? Yeah. So we clarified on Friday, we refined our definition of dV to mean a little change. So now that we're in chapter 4, it means a little change. Yes? What's that? From now on, dV will be a little change in volume. dx will be a little change in x. So that was on Friday, we said we're refining our definition of this thing. We're calling it a differential. And it now will mean a little change. And that was in your reading too. Other questions? Okay. Okay, so if you're, again, going back to the test, if you're disappointed, dejected, despondent, despairing, depressed, all these things, use that to try to use that energy to motivate you to work harder. Okay, so don't have that have a negative effect. Let it have a positive effect. Okay, that you're just going to work harder. And like I said, you need the support. So if you're only going to office hours a little bit or none at all, then it's time to start going. You need that support outside of class to make sure you're staying up with it and you're understanding it as we do it, not just, I can understand it later before the test. Like I said, that's not going to work out. Okay, so I'll just turn up my screen.
Paul ist der Schnellste aus den Blöcken. Jetzt kommt er. Und jetzt ist Usain Bolt nicht zu halten. Nein, er gewinnt. 9,58 Weltrekord. Ein Wahnsinn.
Okay. So, you live in a day and age when you get to see this man who's by far the fastest man who's ever lived. He ran 100 meters in 9.58 seconds, obliterating the world record of all time. So let's talk about speed. Let's talk about speed. He broke the all-time world record in the 100-meter sprint by finishing in 9.58 seconds. How fast did he run? How fast did he run? Besides fast. Really fast. What would you say? How fast did he run? Go, figure it out. Okay, so someone did a calculation and they got 10.44 meters per second. Did you get that? Did he run at a constant speed for the entire race? Is it possible that he ran for a constant speed for the whole race? No. Why? He's got to get up to some cruising speed, right? So you can't in no time all of a sudden be at a speed. You have to start from zero and accelerate, okay? So this 10.44 meters per second is what? It's an average speed, right? For the whole race, okay? He didn't run at that constant speed. So when you have just one speed, all that can be is a constant speed, but he did not run at a constant speed, okay? What does it mean that 1 second after the start, which is what I'm showing you right here, he was running 13.59 miles per hour? What does that mean? So why don't you talk to the person next to you for 30 seconds. What does that mean that he was running 13.59 miles per hour 1 second after the start? Okay. So does it mean if we had a radar gun and we were pointing at him, it would show 13.59? I'm not trying to shoot him, by the way. This is a radar gun. Would it say 13.59? Is that what that means? Yeah, what if the radar gun's broken, right? What if the radar gun's broken? So that's not really the meaning of it. So so here is you saying at the instant when exactly 1 second has elapsed. How fast is he running at this value of time? There he is at this value of time, t equals 1. How fast is he moving? At t equals 1, at t equals 1. Does anybody have a different answer than 13.59? He doesn't look like he's moving to me. This is not true. This is important. This is now we're talking about getting to the real meaning of what does it mean that he's running at 13.59 miles per hour. Here is t equals 1. And he's just not moving. He's there on the screen. He ain't moving. So at this value of time, how fast is he? 0. Really, at this value of time. Okay, so now let me change the question. I changed the question. How fast is he running in this moment of time? So this is going to be a definition for us. A moment of time. In this moment of time, he's running 13.59 miles per hour. So what do we mean by a moment of time? What do we mean by a moment of time?
Continuously moving that small piece of time.
Okay. Yeah? That sounds like a value of time. Someone had another hand?
I started to say, like, the moment isn't paused, therefore his speed isn't at 0, but
So if it's
as he accelerated to 1 second, his speed was.
okay. Other thoughts? Yeah.
There's a correspondence point for how fast he's moving at that point in time.
But what does that, how fast he's moving mean? What does that, yeah. Okay, and that's what he said too. So by a moment, we're going to mean, so if you just take it at t equals 1, there it is. He's not going anywhere. He's going to stand there all afternoon. Okay, so what do we need? We need a little change in time. And so by a moment in time, we're going to mean, so by a moment, it's going to be a small change in the independent variable. A moment is a small change. We need that in order to make sense of speed. Speed requires change. And if time isn't changing, then he's not moving. So we need a little change in time. And that's what we're going to call it. What we're going to call a moment. Okay? All right, so a moment is a change in an independent variable during which the quantities vary with constant rate of change. Okay? So can we get a small enough amount of time so that essentially, essentially, he's going a constant rate, because this is a constant rate. That number is a single number, so it must be a constant rate of change. So we're going to look at a moment is a small change in independent variable during which the quantities vary with constant rate of change. So how does dx play with that? Dx is not equivalent to a moment. It varies within a moment. So remember we said dx is a little change. It's a variable. So it's not equal to whatever we set as a moment. It varies within a moment. So dx could be 0, and then can take on all the values within duration of what we call a moment. Okay, so let's look at the graph of his. So this actually models his, unfortunately, where t is his elapsed time since the start of the race. in seconds. And then the output, or the dependent variable is this distance from the start in meters. This polynomial models that, okay? So if we wanted to graph that, how would we graph that? How would we graph? Well, how do we tell GC to graph? Y equals f of x. And we want to do it just for his race, so it would be between 0 and 9.58. And let's get a good window for this. So remember, we're going to zoom out, especially we want to zoom out on the y-axis. So remember, Option and Command on Mac, Control or Shift gives you just the ability to zoom in and out on a particular axis. Okay, so here's a picture of, as time goes by, his distance from the start. So what I want to do is, I want to zoom in at t equals 1, and let's see if we can get that number 13.59 miles per hour. So what you do is, you hit Shift, and then you click and make a box around where you want to zoom in. See that little box that appeared? And then, so now I'm looking at the graph here. Am I zoomed in far enough to consider this a moment? Why not? It's still curved, right? We want a moment to be, within a moment, we want to see it's essentially constant rate of change. So I'm going to come over here, Shift, click. How about now? I would say one more time. So every time you do that, it will make whatever you selected the full screen, so you're zooming in. Okay, so what about now? So if we chose an interval here from 0.995 to 1.05, we could find his speed during the moment of time at 1 second. During the moment of time of 1 second. And so, what does that show there? So here, let's do. So here I'm at 1.005. And it's a distance of 3.5. Oh, it went away. Okay, anyway, so how would we find his speed in a small period of time, right around 1 second? How would we find that speed? How do we calculate that? It's the same as calculating constant rate of change. So we could get the correspondence point, say here at 1.005, and the correspondence point at 0.995, and then do what? We have those two correspondence points. How will we find then his speed at this moment? Yep, it'd be the change in his meters divided by the change in his time, and then we could convert that to miles per hour, and we would get 13.59, which we don't have time for. Okay, so 1 minute and 30 seconds. Tell the person next to you, what was the big takeaway from today? What was the big idea today? Go. This was it. Bottom of the screen.